you very much for having me. Uh, yeah, as she said, I'm an outreach scientist, for whatever that means. I basically started to work on the Landsat series of satellites as a communication public engagement, and was there for about 18, 19 years. About 4 or 5 years ago, I became the Stella team lead. Very fortunate to do so, and I can go into a little bit of that in a minute. But so what is Stella? How did it come about and all that? So Stella is, like Stacy was saying, is a low-cost, open-source, do-it-yourself handheld instruments, and it came about under the Landsat program. Okay, so Landsat is looking at the Earth and checking the surface reflectance of the Earth. So how is it reflecting light back up to this to the satellite? It's a passive satellite, and so it's using the sun basically as the reflectance source, or the source of light that's being reflected back. Okay. And I was doing, or we were doing intro to remote sensing, sort of 101 in about 5 to 10 minutes, talking about spectral signatures and all this, and using something called the Alta spectrometer. They discontinued that, and Ginger Butcher, my boss, brilliant, and she's like, okay, we have, NASA engineers, scientists, can we develop something similar? Okay. Now, unbeknownst to her, in parallel, there was a gentleman named Paul Morell and his buddy Manuel Lerdo. And Manuel and Paul, they basically had pondered this question and were developing something called basically looking for evapotranspiration. There should be a way by which we could measure this type of thing and mimic it in the low-cost setting. And Paul started to develop that sort of thing. When we got hooked up to him via one of our contacts, Jimmy Acevedo, and we're like, okay, well, here's some. This is what Landsat does. Can we develop an analog for it? And basically, the rest is history with that. I started working on it, and what was developed was the Stella 1.0. And again, it was measuring, the light that's being reflected and surface temperature and all this, and we built upon it, and through iterations and various, hey, we should probably do this, and learn lessons learned. We landed on the Stella 1.2. The Stella 1.2 is something you're seeing in the upper right there, with that is Brad Dorn, who was he's the former head of NASA Agriculture. He's using one right there, and he's got a spectrometer package on there. Okay. So the Stella family includes multiple different types of sensors, and I should say, or instruments. So the Stella 1.2 is a modular package. So it's got a package of sensors at the top that you can take off and put back on some other different sensors. So one of Stella's, basically Stella's logo or motto is, what do you want to measure? Okay. So we want to create that inquisitiveness, that curiosity, and we want people to understand some principles about the engineering and instrumentation, as well as the science and those principles. And we want to do it at an affordable package to make it much more accessible and make NASA much more accessible and approachable, NASA data. Okay, and so that's why these Stellas were developed. And after a while, people started noticing, like, hey, can you develop, what if we could do, say, an air analyzer, measuring like atmospherics and all that, can we measure, say, CO2 and particulate size and all of these sorts of things, and humidity, and because Paul Morell, the gentleman I work with, is, just a world-class engineer, he just, as we're talking, he's developing these things. And so Dr. Nissa Rain was the one who mentioned air quality analyzer. And, and in a weekend, he basically had a whole prototype sort of built. Okay. And then we ran into another gentleman, and he was asking, hey, I know that type of design. That's Paul Morell. And I'm like, yep, that is. And we went back to basically his office because he was like, I want to see what we can discuss with the heliophysics of this. And we got introduced to a fantastic person named Alana Resnick. And between Alana Resnick, Pat Haas, Paul Morell, and I, the Stella was born because, again, we were just spitballing ideas. And as we were spitballing, Paul started putting things together. He's like, well, what do you think about this? What do you think about this? Yeah. And so it was just, it's phenomenal working with these amazing folks. So it's just, I can't, I don't know. I just can't state how wonderful it is working at NASA and meeting just all these amazing people who know so much about things. You know, I don't know much about heliophysics, but I have had to learn through this project so much, and there's still so much that I don't know, and I'm still learning. So it's fantastic. And so we have other ones in the works, like something to go underwater and measure water color and measure turbidity. So, you know, all the turned up stuff that's in the water and all that, and see what's going on there. So some water quality type instruments. We have stuff measuring, you know, like the atmosphere. So, you know, if you start thinking about all of these are all things that we want to measure here, but we are also going to need to measure on the moon, on Mars. You know, we need to measure Mars's atmosphere. We need to see how much sunlight is coming in. How do we power our base that's on there or whatever, right? You know, and how do we grow our plants, and how many plants do we need to grow, and how do we keep track of their health? And we can do that type of stuff, and we're going to have to do it with a bunch of sensors and all that running 24/7. And we're going to have people who know how to do these types of things, know the scientific principles, and exchange things. Apparently, I left my Helio Stella in the other conference room. Thank you very much. So we're going to need to understand these types of things, and we're going to need the next generation to understand these types of things. So how do we do that? How do we go about growing this workforce and getting people to understand this stuff? And again, that's where Stella comes in and creates a fantastic entry point. Okay, and so we've had good success. So what's provided when you're going through these things? We give you online. We give you the parts list. We do not endorse any one vendor or anything like that. We just show you how we built ours. Okay, we give you the build instructions, software, okay, which most of it is drag and drop. A lot of the build instructions, the entry level stuff is literally just connecting some wires. You're not doing any soldering. You don't have to do any 3D printing. We're trying to make it as accessible as possible. Now, as you go up in complexity, so like the Stella 1.2 that I mentioned, that one does require soldering and 3D printing. But the Stellas, the Helios Physics Stella, the air quality, the Stella just basic spectrometer does not require it. And then we're developing activities, and we're working with a community of practice to develop more activities and also formalize them, see what works, what doesn't, what do we need to change, so on and so forth. And also they can help, you know, each other and tailor their activities to the community. Okay. And so we have had success from about, when I say preteen, say third grade-ish or so on up. The young lady down at the bottom there graduated from RIT with her master's degree, doing basically sort of land classification over peat bogs with the Stellas. Okay, the two young ladies in the middle there. One is my daughter, and one is the intern. She's a high school intern at that point, and she's showing how to debug, you know, some of these electronics using a nice digital multimeter. Okay, and the first one you're seeing the students do what we call the spectral mystery activity. Okay, so the idea is you show the spectral signature coming in on the board. So we have a data viewer to do that, and one of the things is you get like a bunch of fun stuff that people would like to look at and have them start to record down field notes, because you're going to have to do that proper field notes. And if you throw in, say, a green piece of construction paper and a plant, okay, they're both going to look, both going to measure as green, but something strange is going to happen in the near infrared on that plant. Okay, it's going to spike, generally speaking, especially if it's a healthy plant. Okay, and I know you were probably looking at the graph a bit in one of the first slides here. So that's one of those things that we're measuring on this graph. So you're seeing something called NDVI up there. It's called Normalized Difference Vegetation Indice. Don't worry, it's a long word. You don't need to know it. for the most part, but basically it's sort of a measure of plant density and plant health, if you will. And the closer it is to one, the more dense and healthy the vegetation is. The closer it is to zero, the close means basically bare ground. And then once it gets into the negatives, that means water. Okay. So you see that green line there, that's NDVI. Okay. And you see where it starts to dip. And the really fun part is that Stella takes measures of the air temperature and surface temperature at the same time. So that the surface temperature, when that NDVI starts to dip, the surface temperature starts to spike. Okay, showing that the plants are cooler and that bare earth that isn't covered by plants is a lot warmer. Okay, and you get to see how static of course the air temperature is, over some of these areas. Okay, and so make no mistake that the quality of the Stella data is nowhere near the quality of, say, a Landsat. Okay, it's not even in the same class. So Landsat would be, say, the gold standard of calibration, validation of precise quality data. Okay, Stella is very much just an entry point to really start understanding these types of concepts. I like to phrase it as like you have NASA Earth observing missions and NASA science data, research, all of that as the tip of the spear, if you will. Okay, and Stella is there just so that you can try and grasp the handle of that spear. Okay. So you can start to tell your own data story with these. Okay. And so again, you're taking measurements from the ground. Okay. And in fact, we've had some people put it on drones. So you see the top team over here that are posing with the Stella 1.2s are part of our NASA Acres crew, Jacob Orser and Allison Breder. Okay. And they're using it for agriculture. Okay, to teach about agricultural concepts, because of course, if we're looking, from space and stuff, and being able to tell the health of plants and all that, one of the big focuses obviously is agriculture. It's our food, and the food our food eats, and we've been monitoring that from space for over 50 years with the Landsat series of satellites, and there's a whole bunch of other satellites that are taking measures as well, but it keeps a nice monitor on our plants. And the really cool part is that, as I was telling you, with the near infrared, when the near infrared is very high and all that, that means that the plant is, generally speaking, healthy and good to go and all that. And as that near infrared starts coming down, that means that the plant is stressed. Okay. Now we can't see that, but we can measure it. Before the plants start turning yellow, brown, wilting, and dying, we can measure that drop in the near infrared. Okay. So that gives farmers and foresters and anyone interested in any kind of vegetation a huge leg up to try and either mitigate or understand what is going on to create that drop. Is it an infestation? Is it a flood? Is there too much water? Is it a drought? So on and so forth. Okay. Is there a disease? I needed to wet the whistle here. Okay. So yeah, let me go back one minute. So there's that group of folks doing agriculture. Now you have these are high school students that I met at AGU. They are using the Stellas, and they put them on drones. They actually combined the heliophysics Stella and the Stella spectrometer. Okay, it's measuring like surface, surface irradiance, and they're flying over and taking measurements. Why would they combine those two? One is measuring incoming solar radiation, and one is measuring the reflected solar radiation. So you can use the differential of the two to try and get, and this is one of their tests, try and get instantaneous reflectance data. Okay, I know it's big stuff, but basically once you get it to reflectance data, you can start to do some real interesting comparisons against different sensors and different instruments, but you need to get it to that point. Okay, so that's one of the ideas behind this. All right, this group down lower here, they actually work with high school students, with undergrads, and of course these are 3 professors, and that board that they're holding up there is basically a sort of a reconstructed Stella 1.2 that they shot up into space. Actually went up into space last week, if I'm not mistaken. Also, Alison Leidner up in the top right corner, she had the astronaut candidates. This was about 2, 3 years ago, um, using the Stellas to take measurements to understand, these different Earth science principles. So really awesome stuff. And you're going to see a quote there by Nick Barbie. Nick Barbie is a fellow that we're working with down in Sarasota, Florida. He has a team of retired engineers and scientists, and they wanted to do something for their community. So they're out there, they're doing basically informal education, like after school workshops, and they're actually starting up a camp for over the summer. And the students are going to be basically trying to look at their local area, their mangroves and all this, and harmful algal blooms. So they have, red tide in there. They're trying to find the beginnings of red tide down in Florida, as well as, studying how their mangroves basically, help their area with all of these different types of problems with the storms, as well as like the algal blooms and all. Okay. And so this is just a few samplings of the different science principles that go into there. There are many, many science principles as well as engineering principles that go into this. So what you're seeing over here is calibration. What is the need for calibration? How do you make things precise and accurate? Okay. So again, Stellas are not the most accurate. Okay. So this is a nice jump to, okay, well, this is not the most accurate, precise thing. I want to go to the next level. What do I need to do next? What sensors, what instruments, so on and so forth do I need to go to? How do I measure the accuracy, the precision? So it's really starting to understand the uncertainties. Okay. And so you see, you see Jesse Barber there over the calibration sphere. He's also the one with the big backpack that looks sort of like a Ghostbuster. Okay. And in the upper image, you're seeing the two high school interns, Manuel Lerdow, who is sort of obfuscated by the pole, and then Paul Morrell, the creator and lead engineer, sort of leaning in a bit to look at the how we're setting up the calibration sphere and all that. So we went through a few different iterations with that as well. And then down below in the lower left corner, you're seeing the two high school students, and then just again obfuscated by one of the high school interns is Dr. Fred Humerick, and actually back there is Dr. Patrick Campbell as well, two of our fantastic doctors, basically, I should say lead scientists for different projects in remote sensing here. Okay. And Jesse Barber and the interns are learning how to do field calibrations with these instruments. Okay, so you have the non-variable calibration in there with the calibration sphere, and then you have the field calibration. Okay, so they're learning these different types of principles, right? And I should say that the backpack that Jesse is wearing is, somewhere up and around, the multi-thousands of dollars, and we're talking probably about six figures. Okay. And so you're not going to trust that to your undergrad, to your middle schoolers and all that sort of stuff. So how do you get, those types of principles and have them really pay attention and find meaning and understanding? And that's, again, where the STEL-LA can really shine and come in, because now you have, something that's low cost. Again, about around $200 or less is is sort of the magic price point to get meaningful data, as well as keeping it open source and all that that we have found. So multiple different engineering disciplines. Again, a lot of these things, they don't require soldering or 3D printing. So we have entry points where you're literally seeing a heliophysics instrument on a piece of cardboard. Okay. Then you start talking about, the engineering and the instrumentation and the layout of these things. So you have in the next picture, you have basically a nice PDF you can print out and drop the sensors on and connect them. And then we have drag and drop programming, so you don't need to do any hardcore programming or anything like that. Now, can you do that? Yes. You can absolutely try and put a different chip on and different sensors, stuff like this, make your mistakes, learn how to fail gracefully and all of that. as I've had to do many times over, trying to program these things and add different sensors on there. And it's a learning process. It's a fantastic learning process. And then you have 3D prints and engineered stuff. So we're making all the 3D prints are available online as well, so they get to learn about additive manufacturing. Okay, so what is the benefit to additive manufacturing versus, say, like subtractive manufacturing and all of that? And what are the two, right? So one of the things that you can do with 3D prints and that we have been doing is rapid prototyping. Okay, does this work or does this not? Does it work for my needs? How do we connect these things? And you can try multiple different variations to come up with your solution. Okay. And so I've done a few videos and all that, and I actually have Paul Morrell actually start to explain these sorts of principles and all that. And then down below, you have the more complicated 1.2, and you have it both in its 3D printed housing and then out showing you all the electronic parts and wiring and all that. Okay, and we actually had those two high school interns. They built 40 of these and sent them across the country, which is fantastic. It's marvelous. They actually finished about 2 weeks early. And not only did they send them out, but we actually did a rotation of basically field data collects with every one of those 40 at least twice. And they just did a marvelous job. So they're in college now, so they're doing great things in college. They're going to have such a good time, and we're actually trying to hire one at the moment. So yeah, multiple different entry points for engineering. Why is this not shifting over? I don't know. Okay, there we go. So NASA connections, and I just threw a few up there. There's Landsat, of course, I've already talked about. PACE, which is a newer satellite that went up that is looking at like water, color, phytoplankton, aerosols, and all of these things. You have NISAR and SMAP, which is doing soil moisture. Okay, and then you have, of course, the many different, heliophysics missions, looking at the sun, and looking at it in different wavelengths, and of course trying to, and again, one of the best things to do with the Stellas as well is relate how we look at these different things and these different measures, and of course why, and why we do it at different scales, right? Why we do it with the small stuff and microscopes, and why we look out into space at large cosmos and nebula and all this in all these different wavelengths, and trying to understand that. But again, it gives you that power right in your hands. And so right here, you're seeing me, and this is Mike Humber, who is with NASA Acres, who is the NASA, basically, that's the agricultural folks that are for the United States. Okay. And we're giving a demo here, basically showing what you can see, the plant health and say even the gas exchange, where the plants are, taking in CO2 and releasing oxygen, all that, so the plants breathe and all that. And that's another measure of this. So if you're trying to, again, go out into space and all that, you're going to need these constant measures, right? You're going to need something easily repairable, easily understandable, so that you can go ahead and keep a constant watch on your food supply, on your air supply, on all of these sorts of things while you're flying out in space and while you're trying to inhabit Mars or the Moon or anything else. Okay. So here we go, operating at different scales. So again, we're working with these folks down in Florida. They wanted to see things at a finer scale, so they have an optical engineer, and we came up with an adapter to put it on any telescope or microscope. And what you're seeing there is the Q2. It's an 18-band spectrometer looking at these things. Okay, now it's going, like I said, it's not going to get you world-class data, but it will get you meaningful data. All right, you're seeing the interns there with Jesse, and we're looking at corn, and talking about how we measure the health of vegetation, and in this case, of course, crops. Using this type of information. Then you have it putting on drones, and then you have this team over here. This is the high school students, and as I mentioned before, this is part of the team that they tested it out on a balloon, and then they shot it up into space about a week ago. Okay, so many different applications: earth science, heliophysics, air quality. You can read all of this. One of the things I love to do is not tell the students anything and have some of these instruments on the table and have them start asking their own questions. as well as trying to answer them. I might give them 3 questions like, what is this thing? How do you think it works? So on and so forth. But literally, I've had students, even at a very young age, start to discover material science. Okay, well, this is green, but how green is it? How yellow is it? How orange is it? Why is it absorbing, why is it, reflecting this much heat, and all that, especially with the surface temperature. And they look at each other's shirts and say they have 2 green shirts, and one's made out of cotton and one's made out of the moisture wicking stuff. And he's like, okay, well, this is cooler than this one. Why is that? And again, really developing that sense of curiosity. Okay. So we have one that you see down in the lower right corner there, and this gentleman is actually using it with his cattle because there's a methane probe on there. How healthy are my cows, right? How much methane are they emitting? All of this, okay? How much particulates are they kicking up, so on and so forth. You're also seeing a graph over there. That graph was taken with the heliophysics, and it was during the eclipse. One of the things that we were looking for is to see if there was any, UV that would be coming through. And at least as far as this ship was concerned, there's no UV that was able to come through during that the eclipse that happened was a year or two ago. Sorry, I forget because my brain is kind of mush because I jet lagged and such, and I need some caffeine. All right. And then, so of course, there's a massive educational impact, and I've discussed quite a bit of this with you. And yeah, down in that lower right corner is Bianca, who graduated from RIT using one of these things. One of the really cool, there's actually, these are all really cool, but you have graduate students teaching 5th and 6th graders over here at the outdoor school, the McCall Outdoor School in Idaho, up in the top right corner. Okay, and then in the bottom, I should say middle right area, you have Inna and Alexa, who are 2 engineers who re-engineered the Stellas because they wanted to put a bigger battery in it, and they created their own data viewer. They basically did all the stuff, and then they went and they taught high school students about all that they did and discovered, and about remote sensing and all of this, and it was just such a fabulous project that they did. And then you see me with over there at the left middle with the NASA Seas high school students, the 4 of them. I'm sort of short, so I might look like one of them, but I'm there in the suspenders and actually the same shirt, so that's kind of embarrassing. But they're the ones who, they had a mission that they were doing, but they took it even further, and they did a poster. They flew it on the drone. They hooked AI into it. They did all of these wonderful things. So obviously there's a massive educational aspect to this. And this is Dr. Nick Barbie, Dr. Timothy Childers, Timothy Childers and Craig Phillips. And these are the class of students that they had at Sarasota for a nice pilot program called Coastwise, where they were taking these instruments out and doing all of these different measures in the mangroves and all that. And he's expanded it now because they loved it so much. And now it's going to become a nice camp down there. And he wants to be sort of the model for how this is done in the communities. So, and here's quite a few of the folks that have contributed to this. There are many, many folks, doing amazing work with this stuff. And, yeah, I can't name them all, but I tried to name quite a few. And very appreciative to NASA and to everyone in there. And if you have questions, if you want to discuss more, feel free to contact me. I'll be out here. And then, and we have a whole community forum. Again, we're trying to build this all together. So, basically, you can put up your ideas, your projects, so on and so forth. The gentleman that I think I was talking up there was Dr. Huici Mangaro Campos. He's down in Puebla, Mexico. He never thought he'd be able to do spectroscopy with his students. And so when these came along, he started doing that, and he's doing graduate level work with his students down there for agriculture. I mean, using these wonderful instruments and all that. So it's again one of my favorite projects that I've ever worked on. I'm very passionate about it. It's I have learned so much, and I have so much left to learn. And that's why I'm here actually at NSTA, the National Science Teachers Association, learning all of this stuff from these amazing folks over here as well. With that, I'll go ahead and be quiet, and you can ask questions and all of that. So, yeah.